Hello, everyone, and welcome to the seminar today. Today we're going to host yogesh-girdhar from Woods Hole Oceanographic Institute. He is a computer scientist and the principal investigator of WHOI's Autonomous Robotics and Perception Laboratory, and an associate scientist in the Applied Ocean Physics and Engineering Department. He received his bachelor's and master's from Rensselaer Polytechnic Institute in Troy, New York, and his PhD from McGill University in Montreal, Canada. During his PhD, Girdhar developed an interest in ocean exploration using autonomous underwater vehicles, which motivated him to come to WHOI, initially as a postdoc, and then later continue as a scientist to start the WARP lab. Girdhar's research has since then focused on developing smarter autonomous exploration robots that can accelerate the scientific discovery process in extreme and challenging environments such as the deep sea. Some notable recognition of his work includes the Best Paper Award in Service Robotics at ICRA 2020, a finalist for Best Paper Award at IROS 2018, an honorable mention for the 2014 CIPPRS Doctoral Dissertation Award. He would be happy to have an interactive communication with the audience, so you may ask questions during the talk, and also he would love to get some collaboration out of this talk, so that would be an option. So it's all yours, Yogesh.
All right, cool. Thank you for inviting me. So the focus of my talk is on enabling vision-guided exploration of the oceans. Like I think vision is one of, I feel like, underappreciated currently in the ocean. Like oceans are primarily sort of dominated by acoustic observations for good reason, right? You can see, you can sense much farther away using acoustics. But there are many types of observations in the ocean which are which are best observed visually, right? If you want to observe, for example, like taxa of some microscopic organisms, or like identify fish or things like that, it's best to do them visually. And however, the challenge with doing vision and then making a robot that is equipped with cameras and in collecting data is that because you can only sense with cameras, you can only sense a few meters away, right? So you need to be much smarter in how you collect your data. You can't just put like a side scan sonar. You can't scan huge swaths of areas rapidly. So you really need to be up close with what you want to observe. So you need to be much smarter. So my talk, I'll try to capture two big topics. I hope I have time. I think I'm already running slow. So for the first, I'll talk about how can we make robots smarter with camera-based observations, and then the crucial addition to that is how do we enable interactive exploration of the oceans with vision-guided robots. So the problem with interactivity is if you have a tether, then yeah, you have constraints of how you can move. If you're untethered, then you have communication constraints. So I'll talk about how we can sort of deal with that through the use of machine learning. And the other idea I want to talk about is oftentimes when you observe with, if you have cameras, we can observe taxas and things like that. So one thing we can actually do as a result of that is build community models of from the data we observe directly. So, and how I'll talk about some work on that. And the thing which actually ties these two seemingly distant works is this idea of we've been working on the statistical model for understanding categorical observations, which are taxa observations or rock types or coral types, or these are categorical observations, how if they're spatially distributed. We've been developing a model to which can digest those, and we can use do some inference and use them in robotics context. And how do we do that? So that's the tying the meat, statistical meat, which ties these two things together. So the challenges. So why is it hard to build vision-guided robots underwater, their acoustic communications do not allow, like, you cannot remotely pilot like an underwater robot because acoustic communication is the only option you have, and that's very low bandwidth. Range sensing, large spatial scales, and like also most of the oceans, we kind of don't know what's happening there, right? So all that basically means we need to come up with better machine learning based techniques, something which other types of sensing modalities, you can still don't have to deal with that, and still you can get good data. But without doing some machine learning, you cannot really do good vision-guided underwater exploration. So here's an example of some of my old work, which I did. Like, this was during my PhD, just to motivate and excite the audience. So this is a robot which I built during my PhD, and it's, when you start the robot, it does not assume any prior knowledge about the world. Like, it's just starting from scratch, no memory. And what it's doing is it's continuously building a visual model of the world, in the sense of, like, it's trying to understand the world in terms of different types of objects it sees using unsupervised machine learning. And then using that model, it's trying to describe the next frame. And also it's trying to compute how much can it explain the next image in terms of all the things which it has seen, right? So it's learning to describe different components, using that model to describe the next image. And the orange dot here, which you see in the front, in the middle, is like in that image, what's the most surprising content in that image. And what ends up happening is, like, then what I tell the robot is something very simple. Just chase that orange dot, as in try to go in the direction where you see most surprising information, right? Go to the part of the scene which is hardest for you to explain given all the data you have seen thus far. And that simple behavior in this example leads us to, like, a robot which automatically wants to stay on top of a coral reef and and like stay away from the sand part of the reef. So it's like it's attracted to corals. The same code running here, you can sort of see it's in some ways a simpler visual model because the background is all pretty sandy and clear. So, but in this simple visual world, like, but if a diver or a fish comes in, they will be the center of the robot's attention, because that's like that's where most amount of new information is. This is not, no additional code has been written. It just works. In this example, what we see is, like, this robot comes across this patchy sort of vegetation on the seafloor, and it naturally wants to stay. You don't have to plan a trajectory. It just wants to stay on this patch, and like it's just maximizes data collection on this patch, because that's where most of my information is. So it's just like a information-seeking robot, which does this, which kind of shows like a curious behavior. It kind of behaves like a little puppy dog underwater. And so, and the point is not like, hey, we should do all ocean exploration like this, but I think maybe this could be like the baseline behavior for any time we deploy robots underwater, where if you don't know what we're looking at, just like, if you see a purple jaguar shark, you should go after that and like stop, pause or whatever you're doing for a second. So the way like a robot like this works is, you have some kind of sensing model, which in this case is a camera. You have an observation model, which is like, understanding that image in terms of different components. And you have a reward function, which is able to kind of say which part, where you should pay attention to. And then you have some kind of system for choosing where, deciding how to get that reward, which is like an informative path planning algorithm. So if you combine, these are different modules. Each one of them is in some way their own research field, but and you can kind of swap them out in different ways, and you can get different kind of adaptive behavior. So I'll talk a little bit about the observation model and reward function and informative pathfinding a little bit, but mainly I'll talk about the observation model, which we have been working on, which makes everything else very simple. So in more recently, we all know about this cool convolutional neural networks these days, which is very easy to train a classifier from it could be from an image or image-like data, even acoustics, audio. Like anytime you have this high dimensional observation, like audio or images, you can build a classifier and out comes a category of observation, right? So you're detecting either a taxa or some morphological type. So you can really think of this as like a new type of sensor, which is outputting categories. And these categories could be like, maybe seafloor textures or like, types of rocks. It could be like, it could be maybe different species of coral or fish you might see. Like it's very easy to build these classifiers using or it could be more recently at the WHOI we have these imaging flow cytobots, which can sort of image these microscopic organisms like phytoplankton and extract their taxa, right? So there are a whole bunch of these types of observations. So their output is this high dimensional category. There could be hundreds or thousands of different species, especially if you're looking at microscopic organisms, small organisms. And the question is, currently we don't really have very well developed techniques to deal with this type of information, right? So oftentimes in the ocean, if we are making a robot which we want to make some decision, is basically working off, maybe is based off the altitude data or like CTD data. All these are like low dimensional observations. You're just looking at 1 or 2 floating point numbers and trying to make a decision. Here, this is like a 1,000-dimensional vector where like we're just showing what distribution of taxa exists. And it's kind of hard, like you cannot use standard approaches to deal with that data, especially if you want to take a few of these observations and try to figure out where should the robot go. So you can think of the data structure as the following, right? That you have a bunch of, your robot is moving around in space. At each point in space and time, it's kind of computing this. Each observation, you can think of it as like a distribution of these categorical observations, which is huge. And what we want to do is we want to come up with a generative model for this data where W is the observation and X is the spatial location. So it's like can we model this joint probability distribution? The problem is that this probability distribution is huge, so there's no way we could just use like a Gaussian process or the usual approaches like covariance matrices to deal with that data. So what we have been doing is what we have proposed is like we factor this joint distribution in terms of these 2 distributions. So we have observations. So X is space or time, and at each one of those observations, so this joint distribution PWX, we factor into this 2 distributions. One is we introduce this idea of this latent variable, which could mean different things in different cases. Like if it's taxa, then you can think of Z as like the communities, right? So we are saying that each location in space, X is space, each location in space, we model it as a distribution over some community, and each community we define as a distribution of the actual observed taxa. And we model these distributions. We have some, to make this learning work, we put some statistical priors on these, like to make them sparse and to make them kind of look at the, use some spatial knowledge to kind of ensure smoothness in space. So there are, you can read about it in our paper, but there we put the right kind of constraints on it to make, to to be able to come up with this factorization. And then the cool thing is, if you do it this way, in some ways, looking at this distribution, how the Z, which is like the latent variable we have introduced, that that kind of allows us to do many things, which I'll talk about. So, So that could, for example, in the images looking for a robot looking down, that could correspond to different substrate types, or in case of phytoplankton, that could correspond to different communities. So we also have, maybe I'll skip over this, like we also have techniques to learn this model in real time. We can do some inference on it in real time. We don't want to deal with batch learning. Batch learning is, of course, you can do it, but in the context of robots, if you're dealing with unknown environments, if you want to have robot deal with unknown environments, we need all the learning to happen in real time, right? So this is very different from most standard supervised learning. We don't want to do that. So we have some ways to, given a stream of data coming in, can we learn this factorization online? And so you can read about that in the paper. So I'll show you some examples of what kind of things we can do as a result of this. So this is a data set from the 100 Island Challenge project from Scripps. And so this is actually a coral reef. This, I think, is 10 meter by 10 meter. So we did a little simulated exploration of this, where we are running that model, which I just described, and the color here corresponds to that Z, the latent variable, which is which in this case corresponds to different types of substrate. So what we see is, in the beginning, it's able to, like, they're mainly there's like coral and not coral, and you use like pink. But what ends up happening is eventually you see all the blue areas is where like the live coral is, and all the pink areas where the dead coral is. And we also see there are these markers, and they all show up as orange, right? So it gets better, right? So more it sees, better it gets, like better these labels get. This is doing this learning on the fly. It's not kind of training with supervised labels. It's just on the fly, getting new data, computing the label for it, and at the same time updating labels for the previous observations, right? And so we have, how can I pause this? Yeah, so this is the sort of the final result. You can see this is where some of those markers were placed. They show up as different colors. All these blue are like live corals, pink is the dead coral rocks or dead coral. And we did not train the system. It just worked without, it's just completely new to the data. So so here's a sort of in a simulated, more called 3D environments. We can also do this in 3D, where we have like this observations which we are taking in 3D using a stereo camera. And what we can do is we can also, again, compute the labels. You can imagine as the robot is going around and is computing, making these image observations, then it's computing these labels. In some ways are giving the robot like high-level context of what it's seeing, right? So if and then the robot can use these high-level sort of labels, the topic labels, to figure out whether it wants to stay there or not, right? So maybe it can either go for, hey, I haven't seen this label much, so I should spend more time here, or it could be like maybe you ask the scientists which label are you most interested in, and it's very rapidly you can sort of tell the robot what to do with a very few examples. So here is an example of it's a visualization of a mission where x-axis is time, and so and this is like again like a robot which is built on a real mission where we use the seabed AUV, and it's taken images like 1 or 2 meters above the seafloor, and there are thousands of these images. And at each point in time, what we see is the colors are these are the labels we compute. That's the stack plot distribution of at that point of the topics we have sort of given. So what you see here is like the mission, it started from here, it went through these red and yellow patches. And so which in this case corresponds to wherever you see red, yellow, that corresponds to rocks. Wherever you see the purple, blue, and green areas, that corresponds to these soft sediments. And these are also the orange, yellow, that's also soft sediments. But this is, if you zoom in, I don't think you see it in this picture. This is like there's some biological burrowing happening here in this area. So there are lots of like tiny holes where worms are. The worms, I guess, have made those holes here. It looks very similar, but there are no burrows here. But so and this is where the sort of the water column is. So very quickly, the robot visually can sort of understand what it's seeing and like, high level what's happening. So cool thing is also as you're computing the labels is okay, but one thing we can also do is compute like this anomaly score, like or perplexity score, which is given this model, what is the probability of the observation which I'm just seeing, right? So you at any given point in time, you take a new image, you try to describe that image given the model you have learned, and you also compute what is the probability of that observation. And so the plot here, the second plot here, it actually shows that the perplexity score. And this can be very useful for identifying weird stuff in the ocean. So in this example, this is the most perplexing image, and this corresponds to this in a scene where there was a dead fish, and there was a whole bunch of different animals were eating that fish carcass, and it was like a pretty interesting scene. So this region corresponds, there was a swarm of crabs which had gathered, and this whole area is perplexing, but it also shows up as a new label, like right, the purple topic corresponds to the crab, and wherever we see purple, like at this time and this time, that's all because of crabs. So, and the cool thing is like it's learned to detect these crabs, although it never seen them before. You didn't train anything, and so this mission was in Panama, and actually we were in a place where we had a submarine. So when the robot came back, we saw this. Where the crabs are, we actually sent our submarine down there, and we saw this huge, gigantic crab migration, which was happening at that point. So this was taken by a submarine of those crabs, which the robot saw. So it's pretty cool. I don't think previously this crab migration was documented. So to put it on you can think of like, this system can be used to really build a map of what the robot is seeing. And you can think of, although the robot cannot send the images to the top side, right? But maybe it can send this map over acoustic communication. So that's one way we can sort of improve, give the scientists some understanding of what the robot is doing. So this is not the best map, but it's because the position information is not super accurate in this. But it kind of gives you the idea that wherever it's the same colors are happening, it's like the same type of environment, and it gets better over time. So, and when you have this machinery, the example which I showed you in the beginning, that's very easy to implement. Like all what you have to say is, so although there is some true distribution of different types of objects in the world shown in this plot, what you want to do is you tell the robot to compute maximize the information gain in the space of the latent topics, the latent variable, the Z, right? So what that means is like, things which are rare, we want to have the maximum entropy distribution is one where we have equal number of observations of all the categories, all the discovered categories. So things which are rare, you're much more likely to be attracted to them, and things which are very common, like the sand background, you're trying to have same amount of observations for each category. So it's naturally attracted to the interesting stuff. So the programming becomes very simple. Just compute maximum information gain observation, turn in the direction of where the most rare observations are, very simple greedy algorithm, and you can have behavior like what I showed in the beginning. So now, so one thing what I learned after coming to WHOI is nobody wants a fully autonomous robot. What really want is you want the robot to be doing whatever intelligent thing it wants to do, but scientists really want the control, right? So, and one way to give them the control is, maybe they just have a map, which I just showed the example of. They can stream that map, but the question is, can we do something better, right? Is there a way we can have give more control to the scientists as the robots are doing? So that's especially useful now because we have our robots are becoming better and better at staying underwater. You can have missions which could be several days long, maybe months long if you're packed with batteries. So more recently, we've been sort of trying to develop this framework. This is very work in progress, so it's not fully developed. We have some simulations of this, but we haven't put it on our real robot system yet. But so the idea here is the following, so this is supposedly some map of the world, and so robot starts from here. It's going along some path, and at each point in time, it's taken images. So given these images, we can use the topic model, which I just described. We can sort of compute the high-level labels for each point in time. And then somehow we want to figure out which topics are interesting or not. So we basically, we ask the scientists up on top whether an image is interesting or not, and use that information. Maybe we just send these images, a few 3-4 images, one image every 10 minutes. We send the scientists whether that's interesting or not, and we use that information to learn a reward model, as in what observations are interesting, and then use that reward model to figure out where to go. Should we go in this direction, that direction, based on what we have seen, and then the question is, how do you select what images to send, right, to the scientists? So and so in this paper, you can go into more detail, but a good approach will. So one simple approach is whatever optimizes the sort of the uncertainty in the world of where the reward is, right? So that's one thing you can do. But actually, a better approach is something where you can also take into account where the robot can go, and what might be interesting in all those, and where is the most uncertainty around that region where the robot could go, and so can we put that all into this big machinery and use that to compute, ask what scientists the right question. And so we put it all, I think, details on the paper, and the goal is here to just kind of get you guys excited. So we have some preliminary results of this approach where we built some simulated world, and we have the robots sort of go around, and these bright spots are where the robot asks some questions. And so starting from again, so each one of these, you can think of this map as some kind of topic map of the world, and some of these categories are interesting, others are not, right? So this is the interest map of the robot, and this is not known to the robot, right? Maybe robot, you put in a robot in a new place, we don't know what there is, so we don't know what the interest map is. But the goal is slowly after the robot sends these queries to the scientist, this is the reward function which the robot is learning, and eventually it converges slowly over towards this true the interest function. So we are able to show that the approach sort of works in simulation. We still have to kind of put it in the real world and try to see how it works, perform in the real world. That's yet to be done. One thing we're also kind of looking at currently is if one problem with the oceans is they are huge, and if you really want to explore, we especially with cameras, we need to deploy lots and lots of robots. And lots of robots, each of them kind of doing that unsupervised learning which I just described we can do. The problem that happens there is each robot, as it explores the world, it might come up with its own labeling of the world. There is no guarantee, because it's unsupervised, there's no guarantee the robot one labels like the background, the number it uses to describe the background is going to be same as robot two. So one of the problems we are kind of figuring out is how can robots come up with fuse the information over low bandwidth. You only have acoustic bandwidth, and so that each robot has like a coherent, some kind of coherent understanding of the world, and like robots can sort of, when an operator says, "Hey, I want the purple topic," all the robots kind of understand what that means, and they can spend their time collecting more information about that type of observation environment. So I'll skip this. I'll skip this video. So this is this is like the platform we have been developing as like a research platform to do the kind of exploration we want to do. So one problem with we are not a hardware lab, but it was very difficult for us to find a robot which is sort of designed for vision-based exploration, and is sort of maneuverable. We want to deploy them in the oceans, in the coral reefs, where there's complex geometry. We want them to like move around with all 6 degrees of freedom, and we don't want it to be torpedo shaped, which cannot be maneuvered that nicely, right? So we want something which can hug the seafloor much more tightly. So we've been working on this hardware platform, which is extremely maneuverable, and it has lots of computing power to do a lot of that real-time computation. And so our goal is to make this project like open as soon as we have like, I think there's certain problems with the robot which we're trying to solve in terms of control. But this is like something we would love to make open and like make it available to everybody if they're interested in doing. So in 5 minutes, I would like to also describe this idea of modeling. So another type of another type of categorical observation, which is like these taxa observations of microorganisms. Like in this case, this is a phytoplankton, right? So this is the wrong slide. Yeah. So many of you might be familiar with the imaging flow cytobot. This is a system which Heidi Sosik at WHOI and Olson they developed here, and this is essentially like a system which can take in a water sample, image it, and it can produce this. They have trained a neural network which currently has more than 90% accuracy over hundreds of different morphological classes, and it can give taxa labels to all the observations of phytoplankton. And this is like example of the kind of data it collects. So this is like I think there's a 7-year timeline where they've been taking observations every 20 minutes, and this is at MVCO. And I think they use the similar sensor or like towing it on a ship to capture the spatial variability. And so the problem here is because as the dimensions increase, it just becomes like harder and harder to understand what's happening. So one thing we were considering, what we thought we could do is, can we use the same type of techniques which I just described, where we factor the observations into these leaving space, but then put these nice priors of sparseness and spatial continuity to extract more meaningful representation of this data. So roughly, we have observed phytoplankton taxa. We want to kind of map that to some kind of community-based representation and do it in a way that we can sort of make the prediction task much easier, like, right? So we can, given just the community description of a particular site, we know exactly what the plankton taxa distribution over there is going to be like, what that is going to be. So again, so we can think of our, this is the timeline. We can think of each point in time as distribution over these 1, 2, 3. These are the communities. So this is community 1, community 2, community some. You have some n sets of community. The community, you don't even have to know how many communities there are. The system can learn that automatically. But each community is essentially a sparse distribution over individual types, right? So the sparseness is important to make it work. But yeah, so that's the general model. And then what we want to do is that each point in time we model it as a distribution over the communities. So here, again, that's a sparse distribution of communities. So if we do that, then we can describe this data as so this top is like the log distribution of the observed data, and the bottom is like the computed community distribution over the same timeline. And so the cool thing is what we see is like there's these cyclical seasonality. We see that there's seasonality in these communities, and which is pretty good indicator that what we're learning is good, because there was no input. Nowhere in the data did we input like the idea of the seasonality. Only the system, the model only accepts the parameters which control the sparseness, and also controls like it only other information which it uses for linking things which are in temporally apart is just like what your neighbors are. It looks at what your temporal neighbors are and uses them for your current distribution. The fact that the seasonality comes out is a good indication that it's doing something right. So if we actually map that to 1 year and average them over a whole year, we see this beautiful sort of community distribution over 1 year. We see there are like these 4 or 5 communities, and there's this spring community. There's a winter community. There's a summer community in like yellow, and there's like some taxa. Some communities kind of stay most of the year from March till December, and so we have like a much higher level view of the data. So, and we can see seasonality, so this is some indication of that what we are doing is like it's the right factorization. So the question is now, what kind of things can we do with it? So here's a plot of like, so one thing again, what we did was to evaluate how useful is this representation. What we did was we tried to learn, can we predict, given the environmental variables, can we predict what the taxa distribution at a particular location is going to be? So we compare it by like a PCA-based representation, factorization, and like our approach, and also can we maybe directly try to use some regression method to directly learn a mapping between environment variables and taxa. So we found like if we instead of directly predicting, if we actually try to predict the communities first using our model, and then given the communities try to predict the taxa, we actually perform much better at predicting what the taxa distribution is going to be. Also, compared to PCA-based or linear methods, this is like the distribution of the discovered communities over time, and we see like a good seasonality for each one of those topics. But if you try to do that with PCA, there's no pattern at all, which actually means any any representation, any communities which PCA-based methods discover, they're like in some ways meaningless because they don't capture seasonality. Just the last, there's a last thing on my thing. So one other thing we did was we try to see if somehow can we use this approach to kind of guide where we sample. So the idea here is like, suppose you want to like find like a hotspot for some taxa which is rare, like, right? So, and the question is, can we, the kind of methods we have, we can compute compute a distribution of like a taxa, even if we don't see it directly, right? So if you know, if I see, for example, all of if you see all of my friends at a particular place, then there's a good chance I'm around, right? So same way, if you like, you know, if I see a whole bunch of taxa from there, if I compute a community label, from there we can kind of compute what the expected probability of a particular taxa is. We can use that to guide the robot. And here we, in this experiment, we tried to compute a hotspot of a different taxa we intentionally hid like the observations of a particular taxa, but to try to compute where the hotspots are of that particular taxa, and we found like there was a good match. So we are able to discover a hotspot of a taxa even without direct observations. And hopefully we would like to use something like that for future robotic missions. So yeah, I'll close the talk here. So in summary, so what I've talked about here is, I think vision-based methods are becoming more and more powerful, like with the classifiers, and you know, we're able to, I think, camera compute with a camera plus a CNN classifier. Essentially, you can think of it as like a new type of sensor, which is spitting out this large number of categories of observations. So like, and that's like a very powerful sensor. It can be used in many different ways, and we described you how we can sort of take advantage of this type of data to understand the world and kind of build robots which can sort of move around with that representation. And really, like, you know, I think hopefully these type of approaches, you know, it's kind of science and engineering is like the chicken and the egg problem. As we kind of make better robots which are able to observe the world in new ways, like that gives us data to formulate new types of hypotheses, right? So which previously have not been possible. So I hope this type of exploration and data understanding will lead to new kind of science. So thank you. I'll take any questions.
Okay, thank you so much, Yogesh. Does anyone have any questions? Also, feel free to unmute yourself and speak. Or you may write that, or you may write the question in the chat window. No.
I have one question here. As you were looking through all the kind of the reward system for the finding the interesting objects, how do you figure out when you've now covered everything in that area and avoid just constantly chasing the same point space?
Yeah, so the system is able to deal with that automatically in the way that more you observe something, less interesting it becomes. Like more observations you have, like all of a sudden, like other things slowly become more and more interesting. So so it's like self-correcting in some ways, the system, right? So because yeah, so more you observe something, less interesting it becomes naturally, and more likely this robot is going to go in a different direction. So assuming everything is equally interesting in front of the robot, is likely to just go around in a random path. Yeah, so I mean, if you feel free to like email me, or if anybody is interested in sort of working on vision guided robots, and or a lot of my code is available, like for if you are interested in modeling community. So we have also, regarding community modeling, we have been apart from phytoplankton, we applied it to microbial data too, and it works pretty well there too. And so one thing I'm interested in doing is like kind of evaluating, like comparing this approach to how other people are doing their community modeling and how they are like looking at that data. So that is something I would love to work with people if.
Yogi, have you been thinking to apply any of those methods on acoustics data?
I haven't much. So there is some. So I think there have been some efforts to kind of deal with like maybe the soundscape data. So I know in coral reefs there's a good amount of so acoustics is different kind of it means different things to different. So there's like the whole thing of like acoustic imaging, like using side scan sonar type thing. But I'm talking about just like hydrophones. So that I guess I've done some work on like not underwater acoustics, but outside, and it seems like these type of methods work there. But that is like a future work for me to investigate how we can use it to understand soundscape, underwater soundscape. That's like one thing of interest to me.
Yeah, I just saw that you did point cloud work using stereo camera. So I was thinking like if you have like point cloud from sonar, then from an echo sounder.
Yeah. So I think it's likely to work if you have like nice high resolution, maybe synthetic aperture radar data. SAR, yeah. So I'm not an expert at that, but if you have high resolution imaging, then a lot of these methods are much more applicable.
Okay.
It's because you're not just the point cloud is not enough, but you also want to infer. You need to have sufficiently rich visual information that you can sort of extract different types of visual features.
Okay.
I've got a question. When you're trying to resolve your images and do the classifications on them, you're treating all the images as having equal quality or equal value. Have you taken a look at potentially stepping back one level and saying, well, here's an image, but in fact, because of the water characteristics or something about it, we know that this is not actually a very good image to work on, so we won't throw that into the mix of what we're doing.
So you're, yeah. So no, we haven't sort of considered. So you're saying like not? Are you talking about like maybe the turbidity is too high, or
exactly, or maybe the angle of the robot was at such a point that the distance from the lens is so large that there's just so much refraction, or any of those sorts of characteristics.
Yeah. So that we haven't looked at like how to throw images yet. But maybe that also, the thing is we don't ingest an image directly. We extract categories of different types of observation in the image and try to use that. So I feel maybe it's mitigated by that. Like, if there's all images blurred or bad, then it might not actually detect. The classifier might not even detect like different things. So it might be, in some ways, you're not feeding in directly the image into our system. So we have that stage, which, but you're right. Maybe there are other things which we can use to throw away things too, but we haven't considered that.
Okay, thank you.
I have a question from Patrick O'Byrne, and it's kind of related to that. We had a speaker a few weeks ago from Florida. Her name was Daria Akinek. I don't know if you've heard of her. she designed a new camera to work better underwater, and I wonder if you've seen her work and how it could improve your robot.
Yeah. So I know Daria's work. She's worked a lot on like computing accurate representation of colors from images, and I think that would be pretty useful if we could like incorporating that into this pipeline, like would improve the work, which we are doing for sure. And so I think once I did kind of try to interact with Daria, but that never panned out. But it's on the list of things. Yes, but that I really like that work, and I think it's pretty cool. And if we can incorporate that, this work would improve.
Okay, so with that, we will conclude the seminar today. Thank you so much, Yogesh, for coming and sharing your work with us.